He's been an electrical engineer. He's got 15 years experience in the field of geophysics, aerospace, and industrial research and design. Right now he's designing industrial metal detection systems which have the ability to sense metal through metal. It's very unique stuff. He's worked for the Geophysical Services Division of Texas Instruments and also at the University of Texas and Dallas. He was introduced to and worked with geophysical concepts which are important to the wireless transmission of electrical power. He also served a stint as a senior engineer in Martin Marietta. There he designed and supervised the construction of industrial process control systems and some advanced space flight testing hardware. He was one of the organizers and chairperson of the 1984 Tesla Symposium, the first one we had, and he also helped out with the 1986 Tesla Symposium, and he was president of the International Tesla Society at one time. He's done many, many more things. I can't even list everything he's done because it's just comprehensive, incredible, and he's really more than what he says he is. He's a very, very competent and capable researcher and one of the best people we have in the field. So here's Toby Grotz. I'll put the microphone back over here. Where's that lever? I'll give you a free tie clip.
All righty.
Okay.
I kind of had a question just to start off with. This is for 10 points. Who's the most famous electrician in the world? That's Lech Walesa. And that's kind of interesting because we're still facing, of course, the problem that Tesla is still virtually unheard of today. Actually, he's probably much more well-known in Europe. But at any rate, I just thought I'd wake you up on that one. How many got it right? Nobody got it right. You're all thinking Tesla today, which is good. One of the reasons we're here is Tesla, and I've got a few things I'd like to pass around. First of all, I've been pushing a computer bulletin board system, which is a Tesla BBS, which we set up in Leadville, Colorado at a local college. And if anybody has a computer and would like to tie on to the Tesla bulletin board network, getting information about Tesla, downloading text files, research papers, etc., or if you have information you'd like to upload that other people can have access to, please dial on. And we're getting about 8,000 calls a year and have about 300 to 150 users at any one time. So the number is area code 719-486-2775, and I've got some flyers here on that bulletin board, so I'll pass these out and you can pass them on, and just a kind of an effort to kind of network and get more information out about Tesla and trade research. We've bumped into quite a number of active researchers on the network, so we're getting connected and acquainted with a lot of other people that are doing innovative research. Yeah, that's got, yeah, 8N1 is the protocol. We've got so many wires up here today, it kind of scares me. Let's see, I need my view graphs. Well, there goes part of the equipment. I had a clip here on my tie. Okay, great. Thank you. Just start off with a little bit of philosophy, because I think that one of the things a lot of us are trying to do is look into alternative aspects of history, personality, physics, etc. And I thought that was a pretty good quote by George Bernard Shaw. The reasonable man adapts himself to the world. The unreasonable man attempts to adapt the world to himself. Therefore, all progress depends on the unreasonable man. And I've met a lot of unreasonable people here, and I'm pretty unreasonable myself sometimes, so I'm glad to be a part of this talk, and I'm glad you could come and listen to us. Now, what I'm going to do today is talk about computer-aided design of Tesla coils. And one of the things that is so interesting about Tesla coils is that they lead on to a greater goal, and that was the goal that Tesla had. He had in mind the wireless transmission of power and the ability to give equal access to all people electrical power. And why would we want to do that? And so just a little bit more philosophy before we get down into the bits and bytes. I'd like you to consider this. If the world were a global village of 100 people, or we could say in this room, if there are 100 people in this room, 1/3 of them would be rich or of moderate income, 2/3 would be poor. Of the 100 residents, 47 would be unable to read, that's this half of the room, and only 1 would have a college education. About 35 would be suffering from malnutrition. At least half would be homeless or living in substandard housing. Of all of you 100 people, 6 of you would be Americans. These 6 would have over 1/3 of the village's entire income, and the other 94 would subsist on the other 2/3. How could the wealthy 6 live in peace with their neighbors? Surely they would be driven to arm themselves against the other 94. Perhaps to spend, as Americans do, about twice as much per person on military defense as the total income of 2/3 of the villagers. So I kind of got into this not only as an engineer, wanting to know more about what it was Tesla was doing, and as a roundabout way had started off with the Lakowski multiple wave oscillator, building those to do research into alternative healing techniques. When I went to the library to find out who was Tesla, there wasn't much there. When I wanted to go find out how to build a Tesla coil, there was nothing there. And so I started looking further and found a lot of people, got involved in organizing a symposium, found out that Tesla had the idea that he could transmit power without wires, and I became very interested in that concept. So therefore, I thought that if we could really see if Tesla's concepts were logical, true, and could be proven, perhaps we would be able to provide a solution to the problems just described. And that is, if we could provide power to the rest of the 2/3, 4 billion people on this planet that don't have power like we do, perhaps it would help humankind. So there's kind of an altruistic as well as a scientific inquisitiveness to my search that's led me to this paper, which is computer-aided design of Tesla coils. Because in doing wireless transmission of power, of course, you've got to build a big Tesla coil, like Tesla did here in Colorado Springs in 1899, as most of you know. So the first thing I'd like to do is start out with one of the best programs. I kind of like to say that it does for the computer-aided design of Tesla coils what the 6502 did to the Apple IIe personal computer market, and that is Jim and Kenny Corum's fabulous computer-aided design program for analyzing and analysis of the Tesla coil that was built in Colorado Springs, that Tesla built in 1899, the master oscillator, we could call it. And that program, by the way, is on sale in the bookstore. And if you want to take a look at it, feel free to browse through the book. It's got an excellent dissertation mathematically. All the equations are there. And I'd like you to just kind of consider picking it up as a reference material and also as a way of getting other people that have computers interested in building Tesla coils. First, just let me describe the coils that are on the market today. If you can see that. There are 5 coils, 5 programs that are available. These are the authors and the names of the programs. The prices run from $40 to $550, and I'm going to demonstrate all of them real quickly. And then we'll turn on the Tesla coil, and I want to show you something that pertains to how we think Tesla did the high voltage rectification of 10 to 20 million volts, was able to charge the tower, discharge the tower, and resonate the Schumann cavity. So first off, I guess actually I'll start over here at this far monitor. I'll take the mic so I don't have to yell. If I got all my wires come with me. This is an original program that was designed and authored by Ron Kovac and others. Ron's here today, and if you really want to know about Tesla coils, I guess I'll have to embarrass Ron and say, Ron, raise your hand. Ron, there he is, right there, the one looking around. That's Ron Kovac. And he put together Tesla coil for the 1984 symposium, and the pictures in the 84 proceedings, which is another valuable set of papers you might consider picking up. Ron was probably one of the first to show what he thought looked like to be the fireballs and ball lightning in the Tesla coil discharges. So this was a program that Ron used to illustrate the design functions of a Tesla coil. It comes up with a graphics section, if you choose that, and shows basically what a Tesla coil looks like. For those of you who are not so familiar with Tesla coils, let me say that basically you've got a transformer which takes 120 volts out of the wall, or could be a 12-volt source. At any rate, you use a transformer to generate a high voltage between 5 to 15 or 45 kV on up. Run it into a primary, which is coupled to a secondary, and you get the discharges. That's basically, for those of you who are non-technical, what you see floating around out in the halls is a transformer, primary, and a secondary type of a coil. So the program goes through and shows you that type of stuff, and goes into a section which asks you to run the design program, which then gives you a list of options you can choose, which you need to choose in order to do your Tesla coil design. We'll go back to the menu here. And the program also has a very good theory section, so that a novice or someone who is not so familiar with electronics can get a basic rundown on how a Tesla coil works, how to build it. Also has a summary of the math used, which is very simple divide and multiply, add and subtract type stuff. So don't be scared, don't be afraid to go out and start building Tesla coils, because there's a little mathematics in it. Basically all you need is a screwdriver and a pencil and some materials, some wire and coil forms. You see there's a pile of junk laying up here, all arranged nicely so that everything goes in and out where it's supposed to, and it costs you next to nothing to build. And going through the math, we'll just go back here to, I'll just point out that there are construction notes here, so they can help you find some, determine how you're going to build, what you're going to build, and how big it's going to be, etc. And that is listed up here. Can we get this front set of lights knocked down? The other one too, there we go, that'll be pretty good. Where is it? TCD, $40, and that's the information. So let me go back to, let's leave this up here. A basic schematic diagram also comes with the program. Okay, I guess you can turn the lights back up. Okay, why don't you knock those lights back down again. That program is running on a Commodore, which are a dime a dozen in the papers these days, and your next door neighbor's kids probably got one sitting around that you can use. So that's pretty easy to access. The others run on IBM PCs, which are used by all people that want to deal in the real world. That's for Macintosh users. Any Mac users out there? Okay, yeah, there are no programs for Macintosh. I would suggest possibly that perhaps we get some programmers together with the program authors, and maybe they can convert over to Macintosh as well. These all run on IBM PCs, which are pretty cheap and not a dime a dozen, but probably 25 cents a dozen these days on the used market. This is the program that the Korn brothers wrote, and the other day it occurred to us, I think yesterday during the meeting, that the Korn brothers may go down in history as a similar relationship as the Wright brothers went down. Excellent combination, a theorist and an experimentalist. And as I understood it, this program kind of evolved because one of them was out trying to build it and kept going into the other one and saying, it doesn't match the theory, it doesn't match the theory. So the other one would sit down and rewrite the theory, and then the other one would run out in the shed and build it. And then finally they got it all figured out how these Tesla coils work. And I think that they were the first people that really were able to, in engineering terms, combine all of the information that was necessary for engineering approach to Tesla coil design. And they wrote a program called TC Tutor. This is the first display screen that comes up with TC Tutor. And it's basically a schematic diagram of Nikola Tesla's Colorado Springs machine. We've got a high voltage input, a spark gap, a primary circuit consisting of a capacitor, resistance, and a primary inductance coupled mutual inductively into a secondary and secondary capacitance. So there is a primary and secondary circuit here. You have to excuse me that this we've got a remote control here that shifts the screen around a little bit, and I may get lost here and have to slow down. The first part of the program enters, let me get my pointer back. The values are input. You can use default values, which are the values Tesla used, or you can enter your own values if you're building your own Tesla coil. The primary inductance in microhenries right here, 57 microhenries on the primary, which is, for those of you that don't know, myself and a number of others were involved in trying to replicate these experiments in up above Leadville, Colorado at 11,000 feet. And we built a coil about the same size, and I measured a lot of these values. So I can personally say, yeah, Tesla was right. He did get the right values in there. Everybody still sleeping? No. Okay. I'll go through here, and we'll just show some output. Okay, we've got 70 kV in and breaks per second. Let's just go, boy, it escapes me. Tesla's, what was Tesla's breaks per second in the 3,000 range? 800. Whoa, I was off. 800, there we go. So he's going to be looking at 249 kilowatts. The Tesla coil we had in Leadville was running actually too many breaks per second, and we were drawing over a megawatt of power. So that was a problem. Okay, now, let's see here. Press any key to continue. Let's see, we're going to find T here, just a second. I may have already ditched the program here. Okay, I've got the old, oh, here we go, that's very nice, okay. Now, what we've got here is the program calculates out what the waveform is going to look like in the resonant circuits. And this is important because this leads into determining the optimum spark duration, and that is based on coefficient of coupling. And I would like to mention to anyone building a Tesla coil, it's very important that you have an adjustable spark gap in your coil. And the reasons for that are varied and complicated, but just take it, if you're building a Tesla coil, make sure that you can adjust the length of your spark gap, because you'll be able to adjust the pulse duration, and that is a very good way to tune your coil for maximum output. Now, let's see if I can get out of this. How do we get to the, I forgot how you get to the Fourier on this. F? Through the F? Find V, find F, okay. Okay, here we go. This does a Fourier analysis of the spectrum of energy within the coil and shows the distribution of the power within the system at what frequency. That's with a Fourier analysis. And that's important because you'll see as the parameters change, you don't get this even distribution of curves. And in the paper that I have, if you'd like a copy of the paper I wrote on this, all this information about the Leadville experiments, Project Tesla, and what we found is all in that paper. So write me a note on a card or on a piece of paper and slip it to me, what you want, and I'll try and get you a copy of the paper. Well, let's just go on here. Let's see, how do we get to the, it's been a while since I used this program. We have to, excuse me here, to the extra coil.
R for resonator.
R for resonator, there we go. Okay, what it ends up in is it shows you what the extra coil will do with the connected to the primary and secondary described over on this particular diagram. And this is the only program that takes into account the extra coil theory. The only one of all the programs that takes into account the extra coil theory, and that is based on transmission line analysis, and it tells you exactly what your step up will be from the extra coil. Here, in this case, if I can find it on the screen, we've got 10 megavolts. Here we go, 9.99 megavolts, spark length, 41 feet. So it is a very useful program. Particularly, there are very few people that build Tesla coils that also build the extra coil to go on it. If you've got a little Tesla coil like you're sitting over here, and you put on an extra coil, you're going to get a lot more spark out of it. I mean, we're talking about a step up possibly of 31 times, as is just demonstrated here. Let me just demonstrate one or two more programs here because I'd like to get more into this discharge circuit over here. The other well, let's see, the other programs, two of the other programs are kind of menu driven. You just enter from menus. I'm loading up one now by a man named Walter Enduro, who lives in southern Arizona. If you want to go down and visit him sometime, we'd be very happy to talk to you. And I won't go through all the tedious steps in the program, but as you can see, you can, actually this is one of the more interesting programs too, of all five of them. Two of them are very interesting in that this one, he's got a list of coils that he's gotten out of TCBA newsletter over the years. And if any of you are really interested in Tesla tidbits and at all interested in technical stuff, here's some TCBA newsletter application forms. It's $20 a year. It's one of the most valuable newsletters in terms of what's going on in Tesla world, who's doing what museums are doing this and that and the other thing. Harry Goldman's established an excellent network, so get in touch with this guy because it's a wealth of information in the Tesla coil building world. And what Walter did was he went through all the last 10 years, 8 years, whatever it was, of TCBA newses and dug out all the coils that are presented in the newsletter. Usually there are anywhere from 1 to 3 coils presented as projects in the newsletter, which is quarterly. He dug out all the information, called up a lot of the builders, and he was able to, I think it's 42 coils he's got in this program. So you can look at past people's performance and history, what their coils have done, modify them to your designs, what kind of hardware you have on hand and can afford. And because when you start buying capacitors, boy, the wallets really deflate fast. The rest of the stuff is easy, nuts and bolts, but those capacitors can break you. Anyway, and you can also build your own, and he goes into some very innovative techniques for building your own capacitors fairly cheaply. So anyway, that's the program. As you can see, it's menu-driven. It goes into inductance calculations, capacitance calculation, resonant frequency calculations, etc., all based on values he's put in there. He also has some fairly good documentation as a readme.doc file on a disk. For those of you that know the IBM, that's basically a text file on a disk that you can access and read. I'll type, see if we can get out of this. Let's see, I think it's, do I really want to end? Yes. Yeah, okay, now we're out of there. Let's see, what am I doing? I got to see what I'm doing here. We've got a program that there isn't that much documentation on the equations used, but well, let me first go over resonance research. Derlin Cox also put out a program here very recently, if I can find it. Tesla. Now the problem is, this program is copy protected and supposedly has some kind of virus in it so that you can't spread it all around. The program, that is, not the virus. And so you got to type into a code number in here, which is interesting because in the literature it says that non-copy protected programs sell twice as many as copy protected programs. Okay, I've got all this information entered in here, the code number and everything. Security clearance granted. Right. All right. Now, that's, you know, every time you go through that, you're going, my goodness. But anyway, this is another menu-driven program. It, you know, it asks you what kind of, how many feet of spark do you want? And if you say 20, by the time you get through, you got a $10,000 coil. So start small and start off at a foot. And it asks you a number of parameters, and so you can pick and choose what kind of capacitance and how big your coil is. And it just goes on menu-driven, much as the last program. Now, let's see. We'll get out of that and go to the last program. Hit Q to enter exit program. Now, I will do. I forgot to bring the executable file, so it's just a canned demo program. Here he's got a little. We had it up on the Tesla bulletin board. We've also got some shareware, two actually just simple basic files up on the bulletin board service that are free for downloading to help you figure out Tesla coil parameters too. A guy just sent them from somewhere on the East Coast. But Colorado Mountain College Timberline Campus BBS system. So I'm just plugging the bulletin board again here, and this was up on the bulletin board for downloading as well. Now, what this program does is separates the screen into the top is all the parameters involved with the primary, and the secondary, and the bottom half of the screen is all parameters involved with the primary. So, my infrared light here isn't working. Is it working? So I got to shift this around on the screen. Here we go. There we go. Down. Okay. Now, can I go left? Or is left right? Yeah. See, left's right and right's left when you're doing this kind of stuff. Well, anyway. Excuse me once more. I'll go back to main screen here. Make sure everything's working. As you as you enter values for the primary and secondary, it instantly calculates other values that you haven't filled in yet. So it's kind of an interactive program that kind of designs online. As you enter a value, several values for the primary, you can hit a button which will tell you, we recommend these values for the secondary, how big to wind it, how many turns of wire, what size gauge to wind it, etc. So it's kind of useful in that it allows very rapid design and redesign on the screen. You say, well, if I change this parameter, what's going to happen to that parameter? So you can go back and forth very quickly and crank out a design by just changing parameters very according to what type of materials you have on hand. Now, I've got a little demo here. I guess we need the lights up that I'll set up.
Turn your computer off.
Yeah, I'm going to disconnect everything. Actually, are there any quick questions on these programs here? Yeah, go ahead.
Do you have any with vacuum tube oscillators?
Repeat the question. Right. There's a note up there on the podium that says repeat the question. I don't even know why they put there because no speaker is going to remember that, but maybe someone will. No, the question was vacuum tube oscillators. The last program I demonstrated does take that into account, but no, there's nothing really on vacuum tube oscillators. Vacuum tube oscillators are Class C push-pull amplifier type design, and so get a book on induction heating and Class C amplifier push-pull design, and you'll get a lot of information about vacuum tube.
George Hathaway, are there any programs that allow the use of Litz wire rather than regular magnet wire, and can yourself or the Corums or perhaps the Andersons in the audience suggest the benefits of using Litz wire rather than regular magnet wire?
Yeah, you can decrease your capacitance and you get a closer packing turn to turn with Litz wire. Litz wire is square wire. So there are definitely...
Multi-filer.
Isn't it square? Litz wire square?
Conductor. Litz wire is
It's multi-conductor. Okay.
Kind of a braided.
A braided. I always...
It's braided with each strand is insulated from the other. It's only connected at the ends.
Yeah, I wouldn't do that. I think you get a lot of capacitance in your secondary. You could design with it, but I wouldn't personally. I think that the square wire, what do they call the square wire?
Square wire.
No, there's a name for it. Yeah, you can't kid me.
Do you have the term radius of curvature in your computations that you're using one of the smaller coils, one of the extra coils, that
Radius of curvature
yeah, radius of curvature.
on the secondary, primary.
When you're winding it, there's a proportion.
That's the rate. Yeah, it's taken into account in most of the programs.
So that term actually.
No, the term isn't used, but it's kind of in the mathematics.
Which of these, if any, include calculations for the extra coil?
Just the TC tutor, out of focus. There we go. The second one down.
Any problems for pacemakers?
Any problems for pacemakers? Yeah, there are. Yeah, right. Move to the back. Yeah, this is a very, very weak. It's only 32-watt coil, so.
It may reprogram it. It wouldn't hurt, but it may reprogram it.
Yeah. Let's not take a chance. Let me set this other deal up here, and what I'm going to do is show you what I think Tesla used to do the wireless transmission of power, the missing key, so to speak, on how you get all the charge up on top of the tower and keep it there without the charge getting back down so that you can control the discharge from the tower in order to resonate the Schumann cavity. And I can show you a picture in the book which I think shows what he was doing. So if maybe a couple of you guys just kind of help me just clear all this stuff off the table, we'll just pull plugs and turn stuff off. Just put it under the table. Yeah. What's that? Yeah.
Yeah.
That was built for speed, not for. Let's see. Clip lead, but I think we can get by without it. This was built with 1899 components. That's a doorknob off an old hotel in Leadville, real historic, built by one of the Silver Kings. Actually, it was the Silver Recession that killed those Silver Kings that also hit J.P. Morgan, that caused J.P. Morgan to withdraw his funding from Tesla. So, what we have here is a coil that is going to discharge to an elevated capacitance when I turn it on and plug it in. I don't know what happens. Plugged in. Let's see. Where are we? This is basically built with just a relay as a vibrator interrupter to switch 12 volts into a car ignition spark coil. And the power consumption on this is very, very low, which makes it very, very light and easy to carry around. Now that right there was actually one of the coils described in the co-author of this paper, who was Jack Kuchar, author of the Tesla Handbook. The Tesla Handbook, if you want to know how to build Tesla coils, is on display in the bookstore. And he's also coming out with Volume 2. It's kind of a step-by-step approach to building Tesla coils. So if you're interested in Volume 2, I've got some information on Volume 2 that he's come out with. But this coil was just kind of based on Jack's design. Now what happens is, let me get a clip lead. Here we go. Yeah. Yeah, I pulled that monitor. Did pull the plug on it. It's still going? Oh, okay. Wrong plug. Thanks. That would be a bill, wouldn't it? 50 cents for a local call here. Okay, you'll see that this is an electroscope, and this device here will spin when there's a charge applied to it. As you can see, there is a charge being applied to that electroscope.
Doesn't like ozone.
This is the smallest Tesla coil you can possibly build.
Just hope the sprinklers don't come on.
Toby, there's one, is that one?
Yeah, yeah.
Maybe you can move back.
Tell you what, will someone grab this table here and we'll just... Okay, that's all right. That's just a screw. Okay, maybe we'll get away with that.
If that doesn't work, move it real close.
Yeah.
Yes.
Well, we'll give it another try. If not, I'll just have to describe it to you. Now notice that every time there's an arc between the two, if you can notice this, it's kind of hard to notice from this size of an audience, but every time there's a spark between the two, this guy will discharge. This electroscope will discharge. The charge is not being held on the elevated capacitance, which is the tower above the laboratory in Colorado Springs. You'll see a big tower going up. We call that the elevated capacitance. But you have to charge that up. But you can see that if there's an arc going up, which you really don't see because it's happening so fast, there's an arc going down. So all the electrons are flowing up onto the sphere, and at the same time, on the other half of the cycle, they're flowing back down. Now what happens is if you have a little point here, it's very, very easy for the electrons to flow off that point and get to this sphere. But it's hard for them to jump back down. So in effect, what you can do is you can pump electrons onto this elevated capacitance. And you have in effect, a rectification that takes place. It's a 10 million volt rectifier, basically. And if I can get this working just right here without the electroscope, we'll see that the charge can build up until it discharges, and we should be able to get pretty good snap because I've got two capacitors up here to kind of add to the capacitance of the sphere. The sphere is not very much capacitance, so I stuck a couple of 500 picofarad doorknob capacitors up there, 30 kVs. Just hold on 1 second here. Okay, you see every once in a while there's a short snap. That is this whole system discharging. So it builds up a charge, and then it reaches a point where it actually discharges. But during the time that it's not doing that bright spark there, right there in between, it's building up a charge. So if I shut this off, and I put a wire across this capacitor, everybody see that? You can see the spark. Okay, so therefore we ended up with an elevated capacitance. You can turn the lights on. Thank you. We ended up with an elevated capacitance that was charged, in Tesla's case, charged to 10 million volts, and then discharged, charged at 100,000 times a second, and then discharged at 7.8 times a second. And I didn't mark this. We just kind of decided to throw this in at the last minute because if I went through all that computer-aided design stuff, I'd be sleeping by the time I got through. And basically, here is a picture of Tesla's point-to-plane discharge, what I believe was his point-to-plane discharge, one of his pictures. There's another picture in here that's more dramatic, but you see he's placed little points all around the extra coil here. So it's real easy for electrons to spray off of this extra coil. That charges this tower in the center, which raised up above his laboratory, to a point where the charge cloud, all electron cloud, grew up in a big sphere around the tower. At a point that he constructed a second tower on the side of his building, where he had a big heavy wire going to ground. And when the charge built up big enough, there was an electrode on the side that all the electrons could then escape off the tower to ground. So that was his 8 hertz oscillator. And the reason that I think that he did it that way is because of the data that Jim and Kenny cranked out that showed that yes, he had utilized the Schumann cavity, and based on his measurements, the experimental data fit all the equations for the Schumann cavity. But also, back in New York City, Leland Anderson has some slides that show, hanging on the wall at Wardenclyffe, there were a number, we're talking in the 10s to 20s, 30s, 40s, pictures of different various designs of X-ray tubes that he had tried back at Wardenclyffe. So his second idea was to use a single electrode X-ray tube to ionize a path so that he could direct the discharge along an ionized path. But I do not believe that he did it in Colorado Springs, because the pictures of the laboratories only show one X-ray tube that he had at that time in the laboratory. So he wasn't big into the X-ray tubes until he got to Wardenclyffe. It was at Wardenclyffe that he was trying to use the X-ray tubes to do the high voltage rectification and directed discharge. And it was in Colorado Springs, I believe, that he was doing point-to-plane. So what that means is that it should be fairly easy to duplicate Tesla's experiment just by building a coil the same size he had, putting up a tower, and using a point-to-plane discharge. You should be able to resonate the Schumann cavity, improve the principle of wireless transmission of power without having to go further into the esoteric design of X-ray tubes and laser-triggered switching, which is also a newer technology that would probably work with this type of system. So basically, I think that's it because it's 1:49.
Did he also,
We have
Toby would have an X-ray tube or a neon tube?
X-ray tube. He was using X-ray tubes.
Did he also have a pendulum for discharge?
It could have been. It could have been. I don't know. That's something that I've heard before, that there might have been a pendulum controlling that. Yeah, he could have had a pendulum, because the pendulum would have come in close to the cloud too. He might have had more accurate. Yeah, he could have had more accurate control of when it was going to discharge that way. I built a little spark gap into this circuit that also shows that you can control the frequency of discharge off that ball as well by adjusting those electrodes. So he could have used an electrode type of control on his discharge frequency. Any other questions?
If you try to power a whole country this way, would there be effects on the health of the people from all that radiation coming out?
Yeah, I think the health of the people would vastly improve. The question was, would there be any effect on the health of the people of a country that were getting wireless transmission of power? And if you think of all the amenities we have that are supplied by electrical power, which include access to hospitals, access to flushing toilets, access to sanitation, to food, that any country that was getting electrical power, their standard of living would increase by a factor of 10. To really address your question, what I know you're asking is that electromagnetically speaking, the field strength generated in the Schumann cavity by an 8 hertz system would be 1,000,000 times, actually I think the calculations are like 1,000,000,000 times less than the 60 cycles you're being exposed to right here in this room. So there's not to worry. If that's a problem, we should all be dead from the 60 cycles. So we don't think there's any harmful environmental effects whatsoever. You get more energy off a lightning bolt affecting your body than you would off a wireless transmission of power system.
What was the commercial power input to the 1899 experiment in Colorado Springs? Was 60 cycle power available?
The commercial power input is the question. How much power used 1899? About 250 kW, and I don't know whether, I imagine that was 60 cycle. 50, 60, 133 cycles, yeah, okay. And it was a downtown generator, downtown Colorado Springs.
Have you calculated with this new corporation, have you come up with any calculations the amount of energy that it's going to take to put into the Schumann cavity before you can detect it, to know that you've done it?
Yeah, it's basically on the order of probably less than 100 kW. It takes very little power to get it going. If you'd like more information about wireless transmission of power experimentation and where it's gone from there, there were a lot of these brochures that were put out last night. I don't know what happened to them. They're all gone, so I assume everybody got one. We've set up a nonprofit research corporation to pursue the research. And actually, in this picture, Jim Corum pointed out, in the picture on this, you can see a little fireball, an actual ball lightning type of deal, right above one of the coils. It's a little dot in that coil. So if you'd like more information, just keep in touch with us. It's got the BBS number in there, and we'll see what happens. Another question.
So once you got this resonator going in the Schumann cavity, how many people could you supply with that?
How many people could we supply?
Many stations doing the same thing, or one station?
It's a possibility that, well, one station, you know, how many stations do you need? It gets to a point where you get too big, it costs too much, but, you know, possibly in the tens to hundreds of megawatt stations, megawatt of power could be transmitted from a single station, so that you could hook up into the grid system here in the Rocky Mountains and transmit power to any number of stations around the world, all receiving simultaneously. You could also set up stations on the East Coast, in the mountains on the East Coast. The altitude helps you, just in terms of, well, there's some physics involved, but it's good to be at a higher altitude than a lower altitude. So you could supply as much power as we have. In that flyer I'm handing out, there's some rough calculations as to how much power we have available in this country, excess power generation capability. Particularly at night, we have a lot of excess power capability, so we could transmit power. Utilities could sell their power from the United States to any other country in the daytime side of the planet that was wanted to buy it, giving the utilities new customers.
Do you have any books you can recommend that explain what the Schumann cavity is, if you don't know?
A good book to explain what the Schumann cavity is. Yes, in the 86 proceedings, the transient propagations of ELF pulses in the ionospheric cavity by Corms and Adinajad explains the Schumann cavity very well.
Compared to computer code, you see how well they agree with each other?
The computer code, yeah, we have kind of, not really compared the code to see how well the programs agree. The question was, how well is the code, do these agree? I'd say they're within 80% of each other, because when I crank out the equations for this coil on one program versus another program, they don't match. They come close, but I'd say they're within 80%. And it would be kind of nice to get all the authors together to bear their equations to each other and get more into, for instance, a lot of these programs don't calculate mutual inductance. That's something you have to measure and enter. It doesn't take into the effect of geometry and calculate some things. So there's still work to be done in the computer-aided design and test of coils.
What would the receiver look like for the user of the energy component?
The receiver for the user of the energy, that's kind of under discussion. It really hasn't been designed, except that it would probably, what Tesla used was a 1,000-foot antenna connected to a fairly large apparatus. So it would be a fairly big-sized apparatus. It's not something you're going to stick on everybody's house. There's also another method of doing it, which would use considerably more space, but probably be a lot more efficient. And I think it's 10:54, so I know the next speaker's probably needs to get ready to come up here. So I probably ought to take one more question. Tom?
Just in case anybody wants to learn more about the Schumann cavity, we got this booklet on sale at bookstore, and actually about 3 pages.
Tom Valone says in the bookstore there's a book on the Schumann cavity, 3 pages on the Schumann cavity in that book there if you want to know more about the Schumann cavity. By the way, I want to say that this kind of, you know, gets in my craw, so to speak, a little bit. I don't know why, but it does, so I'll tell you about it. There is a term bandied about in the popular Tesla literature called non-Hertzian waves, non-Hertzian electromagnetics. Non-Hertzian is a term that Tesla coined. So perhaps I'm too much of a purist, but when Tesla used the term non-Hertzian electromagnetics, all he meant was electromagnetics that was inside a resonant cavity, like a microwave resonator, like a microwave oven, like the Schumann cavity. It's still plain old, ordinary, everyday, engineerable electromagnetics. It's just that it didn't shoot out of the cavity like a higher frequency wave would, which he called a Hertzian wave, but it would remain in the cavity, so he called it a non-Hertzian wave. But they obey all of the Maxwell's equations. There's nothing esoteric about them. They're not scalar waves, they're not longitudinal waves, they're not this, that, and the other thing. A non-Hertzian wave, which Tesla coined the phrase for, is basically a standard electromagnetic wave. So I'd kind of like to ask that those that are out there claiming that there is such a thing as a non-Hertzian electromagnetic wave and that's connected to UFO drives and free energy devices, that's not at all what Tesla was doing. Tesla was doing standard engineering physics. There's no evidence or indication whatsoever that Tesla was doing anything other than standard engineering